Welcome everyone, presenters, audience members and online viewers to the video science seminar, How Good Are Current Climate Models for Predicting Agricultural Impacts in Africa and South Asia. The seminar is organised by the CGIAR Research Programme on Climate Change, Agriculture and Food Security, also known as CCAFS. It is the first in a series of 4 online science seminars this year. We're delighted today to have 2 excellent speakers with us. Let me introduce to you Richard Washington and Mark New, both professors of climate science at the School of Geography and Environment here at the University of Oxford. Professor Richard Washington is engaged in research on climate change and variability in Africa and the global ocean basins. His research evaluates how mechanisms of rainfall are represented in global and regional climate models and how these mechanisms work in the real world. Professor Mark New has since mid-2011 held a joint appointment at the University of Cape Town, where he is director of the African Climate and Development Initiative. His research focuses on climate change detection, processes, scenarios, impacts, and adaptation. The science seminar today will be divided into 2 parts. The first part will be a 30-minute presentation of new studies that assess the performance of climate models in representing the current and future climate of East Africa, West Africa and South Asia. The second part will be a 30-minute question and answer session where you can ask questions to our presenters. During the seminar, online viewers can type in questions via the chat on the CCAFS website. You'll find it below your browser window. If you experience bad video quality, you can link to the webcasts which have been adjusted to fit for a slower internet connection. First of all, let me give the floor to Richard. Over to you, Richard.
Thanks, Sonia. And thanks also to Philip Thornton, who commissioned the study to us in Oxford. Very grateful to CCAFS for the opportunity to look in the vast model data sets that now exist. And acknowledgements to those who helped on the East and West African study, namely Helen Pierce and Matt Horcroft, who did much of the computational and writing work behind the presentation. So if I could move on to the layout of the talk. We'll start with West Africa and the Sahel and move on to East Africa, and then Mark will finish up with the IGP. We'll talk about the background climate, how the models deal with that climate, and we'll have a look to see what the agricultural impacts look like at a very basic level. And if there's time, we'll get on to some things that are in the pipeline with respect to climate modeling. So let's start with the annual cycle of rainfall. This is the mean monthly climatology. We're in February, March, April now. You can see the rains moving up and down Africa through to the end of the year. In the case of the Sahel, they pass from about June to September. And in the case of East Africa, that we'll get to later, there are 2 rainfall seasons, the long rains from March to May and the short rains from October to November. So let's start in the case of the West African climate. This is a complicated and rather delicate climate system, and in the next few slides I'll uncover some of the reasons for that. This is a plot of long-term mean winds for the region, going from about 5 south of the equator through to across the Sahara 35 north, with the vertical coordinate being height. And in this case, the warm colours show the northward wind, which brings the water vapour to the West African and Sahelian region. And it's an incredibly small and shallow flow. And what the plot doesn't indicate is that that feed essentially happens by night during the Sahel. So it's quite a delicate mechanism to model, and it's even more delicate in the case of the future projections. And of course, that flow meets the very strong and very dry outflow across the Sahara in the form of the Harmattan winds. Now, if we ask the question, how does this region interact with the global oceans? The answer is that it's a receiver of many signals, and the mix between them is both nonlinear and complicated. In the top plot, we see that warming over the Gulf of Guinea region, for example, leads to more rainfall along that Guinea coastline, but less rainfall in the case of the Sahel. If we look in the case of the Pacific, warming in the eastern tropical Pacific leads to drying across much of the Sahel. And then in the bottom plot, this contrast in ocean temperatures, which was first recognized in a Nature paper in 1986, between cooler temperatures in the south and warmer temperatures in the north, or vice versa, is related to marked changes in rainfall across the Sahel too. So that putting those things together, what we find is a really extraordinary time series of rainfall for this region that's characterized both by interannual variability, but also by this very long downturn in rainfall of about 30% lasting many decades. And this is one of the most striking geophysical time series that we have of the planet. So it's a real receiver of signals, this region. Part of the story probably lies in the land surface feedbacks over the Sahel as well, which I haven't yet mentioned, and which are an area that's receiving a lot of attention at the moment. But the complicated mix of ocean temperatures is sufficiently challenging as is. Now, if we ask the question, how well do climate models simulate this complicated region, we can immediately see, if we plot up the long-term mean climatology in the observed data set shown in color in the bottom left, and compare with the coupled climate models, that many coupled climate models have a hard time reproducing that distribution of rainfall. Many are too wet, many put too much rainfall over the oceans, and many have maxima of rainfall that aren't matched with respect to the climatology. If we complicate that a little further, and in each of these plots we've got calendar months along the bottom axis and latitude along the vertical axis, going from the Gulf of Guinea through to the dry Sahara, where the rainfall essentially reaches zero. We show the observed in the top two plots, and the coupled climate models you can see in all the other plots. So what you're looking for is a match of color in terms of the onset of the rainfall and the cessation of the rainfall, and the limits to the northward extent of that rainfall to the southern edge of the Sahara. And you can see immediately that most models are too wet. Most models start their rainfall too early, and many end too late. And some, without picking out any particular name, make a complete mess of the process. So we can extract and quantify and tabulate that data in a table which shows the onset and the end dates. For the observed, we're looking at onsets of about June, cessation sometime in September, a mixture of dates really between the observed data sets. For the most parts, the models, as I mentioned, start much too early, some as early as May, and many end in November rather than September. So essentially first order errors with respect to the annual cycle of rainfall over the delicate region. Now, mapped onto that is this desire to understand what will happen to rain-fed agricultural production over the region. So we had a look with respect to the coupled climate models that I've been showing you. And the way that we did this was in this very simple methodology where we selected some crops important to the region. We established the climate-related limits to cultivation of those crops. So climate only, not to do with where they're actually grown or what soil types would dictate, simply extracting the climate component. The next question was to ask how well those models replicate those climatically defined regions. So having defined what crops might be sensitive to with respect to climate, how well can we repiece the extent or the domain of potential cultivation in the models? And then we had a look to see how those change in the future. So simple test really of the coupled climate models and a simple question at the end. These are the crops that we picked out in the case of West Africa, ranked in terms of their monetary value to the region and shown with and without the contribution of Nigeria. I'm going to settle on the top ones, cassava, millet, and if there's time, rice. We had a definition, quantitative definition of the thresholds, climate thresholds, which define the extent of the crops, and you can see some of the descriptive components of those here. So how well do the models reproduce the viable areas of cultivation? Well, notwithstanding all those painful areas that we saw in the biases of the model, they actually do quite well. And that's because instead of looking at climatically defined biases, where we might get upset, for instance, about a 2-degree difference between model and reality, or a small percentage in rainfall change, we're now working within an envelope that a plant might care about. And we see that it's pretty much the case that many of these important crops, there's very much a tolerable comparison between what the observed climate would dictate as the viable area and what the model will allow. There are differences, of course, and in the case of the northern edge of the Sahel, there is an important difference in many of the crops. And many of them, for instance, might be too extensive because of the wet bias in the climatology. What happens then if we look into the future? The report contains details by decade on how this unfolds. This is just a mere taster that might encourage you to look deeper. In the case of cassava, the domains don't change significantly provided you average all the models together. That's not saying anything about the quality of the production or the quantity of production. It's just the area within which the productivity would be viable. But there is, if you look in particular models, a great divergence between the results. So in some cases, for instance, with models showing a wetting of the Sahel, the area for viable cultivation expands rapidly. In other cases, in the drier models, it might move by as much as 2 degrees southwards. So a lot of uncertainty in this particular crop with respect to the northern extent, northern limits of growth. The same story really with millet, in the sense that the divergence isn't very large, provided you look at the ensemble average. But then if you look at extreme members of that model group, then we find very big differences. And some concern also that the optimal temperatures of 28 degrees begin to be exceeded in just about all models and all the domains. And those thresholds become exceeded very early in the century as well. So time-wise, unraveling of the change in viable areas is important in this case. So what's going on in the case of the Sahel? Well, underlying what we've been showing here is a great difficulty that the models have in simulating the region well. That gets masked a lot when we have this envelope of tolerance within the crop perspective. But if you look in the literature and the way that the problem's being dealt with in the literature, the divergence between the model members of that ensemble group are really what needs looking at. So here's a study by Kerry Cook and co-workers who established the workings of 3 models. They picked the 3 best models with respect to the current climatology. And essentially, on the basis of the performance or the ability of those models to repiece current climatology, concluded that the best estimate should be that the region might dry in the future. A contrasting approach would be to take all the models, as I've been doing in the case of the ensemble results I've been showing. And in that case, if you melt all the models down and produce an average, then the Sahel becomes wetter. So at the moment, it is very much a choice as to how you deal methodologically with the envelope of uncertainty in the case of particularly in the case of the Sahel. Now, there is a silver lining to this, and this is just one such silver lining. On the left, we have one of these plots which shows latitude by month and the rainfall onset and the observed in the left-hand case. And in the right, the latest version of the Met Office model in the UK, averaged out over a number of years to reproduce that rainfall onset. And there's been a jump in capability in that particular model, in this version of that particular model, to replicate the climatology, which is very hopeful indeed. Okay, on to the East African story. Again, we'll work through those basic questions about how well the models cope with the region and what they show us with respect to climatology. And I think I've got about 5 minutes left. Good. Okay. Again, a sequence of plots for individual models in each panel showing the months of the year from January to December and the latitude of change. And you can see the arrival of the rains in 2 seasons in the case of East Africa. The top 2 panels show us our best estimate from what we might call the observed, and then individual climate models from the CMIP3 model grouping are shown. Some make a total mess of the region, as you can see in this case. That wouldn't be worth considering. But for the most part, the models have a reasonable capability in terms of reproducing East African climate. They don't suffer from the difficulties that seem apparent over the Sahel region. So the same process with respect to the methodology for the region, choosing the crops based on their contribution to the region and establishing what happens in the future. In this case, we worked through a number of crops. I'll just focus on a few, the top ones in bold in the diagram: maize, cassava, and bananas. How well do the models reproduce the area? In the case of East Africa, they seem to do better, certainly, than West Africa. Although in the case of particular crops, for instance in banana, the prediction of the area which is viable for cultivation is actually smaller than the area which we would get from working with the observed data alone. Other crops are much more forgiving, like cassava, which cover the region very broadly, and the models are able to replicate that. And then maize, which is limited to the northern part of the domain, is replicated again when we look to see how the models do. Okay, so this is one example of the extent of cassava and how the models would indicate where in this particular region the cassava could be viable for growth. You can see the basic shape of the domain is replicated in many models, in some not at all, but the precise conditions and the precise shape do differ from model to model. But on the whole, it's not a total mess. There's something to work with, most certainly, there. What's going on in terms of the future? Well, here we see for the March, April, May, that's the long rains in East Africa, an axis of warmer temperatures in this sector and wetter conditions in this sector of the plots. And in the case of March, April, May, for the business as usual scenario into the future, most of the models land into the warmer and wetter sector. Not all, but many. And there certainly isn't the same sort of split that we see in the case of West Africa. And in the case of the short rains, October to December, the models land much more happily in the wetter domain. Bear in mind, these are global models. So what happens when we look to the future? In the case of banana, there seem to be opportunities for growth and expansion of the region, which is interesting. It's perhaps what we might expect given the warmer, wetter climate indicated by the global models. Maize isn't predicted to change significantly, but only in a contraction in the small region of Sudan. And in the case of cassava, there's some contraction of the northern boundary of cultivation. And I think that what this methodology, simple as it is doing, is connecting a very simple test of the viability of crop growth with these global models. And I think what it's doing is indicating the areas where there's scope for doing much more detailed studies. So in many cases, it might not be worth it over a broad domain, but certainly near the fringes, we would know to concentrate effort in the future. Okay, so this is an example then of how the individual models would project the domain for cassava in the future. And you can see that the shape, the extent of that envelope in the future is very similar between the models. And now on to IGP.
Thanks, Richard. So pretty much the same procedure for the Indo-Gangetic Plain. We'll start off by just describing a little bit the problems in representing the climate of that area. So, Torben, next slide. Thanks. So in terms of the basic climate of the Indo-Gangetic Plain, there's two main sources in terms of water for agriculture. The first is the well-known Indian monsoon, which produces approximately 70% of the local rainfall in that plain. So the season from May through to August is where the majority of the water that falls locally is available. And it also provides, the monsoon also provides then a delayed supply of water through the through precipitation in the Himalayas, which then acts as a source for the Indus and the Ganges rivers. And that water then flows down towards the end of the monsoon season and actually provides water for irrigation as you exit the monsoon season. And then the second aspect of the basic climate of this area is winter snowfall, again in the Himalayas, which provides a store of solid precipitation over the winter that is then released in the dry season as melt. And that actually comes from a different source, which is most of the winter snowfall comes through mid-latitude westerly disturbances. So in effect, we've got two different systems that are supplying water to the Indo-Gangetic Plain. The most important is the monsoon, but in certain regions, particularly in the in the Indus, where a large proportion of the dry season flow is due to snowmelt and glacier melt, what's happening in winter in terms of snow accumulation is also quite important. Okay. The other issue that we have with the monsoon, and particularly with its variability, is similar to what Richard was talking about in West Africa, is that there are a lot of external and sort of proximate and more distant drivers that control the timing and the intensity of the monsoon. One of the most important is the El Nino Southern Oscillation phenomenon. So when you have an El Nino event, you tend to have a reduced monsoon rainfall, which is driven by enhanced subsidence sinking of air over the Indian monsoon region. But there's also a pattern that, depending on the type of El Nino event you get this signal or not. So if the strength of the El Nino event is more located in the central Pacific, then that tends to not affect rainfall as much as if it's located more always get this wrong, to the eastern Pacific. So the type of the El Nino event actually controls whether you get a monsoon failure in an El Nino event. What's happening in the Indian Ocean also influences the more regional monsoon circulation. So variation in the Indian Ocean is important. Eurasian snow cover is important because the monsoon is driven by heat contrasts between continent, the Eurasian continent and the Indian Ocean. So if you have a particularly high snow season, that can affect the strength of that circulation. High snow season, and even signals from the North Atlantic can affect that circulation. High snow season, and even signals finally more recently, the Asian brown cloud aerosols are thought to be interacting in terms of the local sort of radiation balance in the monsoon system, and actually have different effects between pre-monsoon rainfall and core monsoon rainfall. So that those aerosols are actually changing the characteristics of rainfall within and outside of the monsoon season. So essentially what all this boils down to is that if you want a climate model to represent monsoon rainfall properly, and particularly variability in monsoon rainfall, it's got to get a lot of these things right internally for you to have some sort of confidence in the ability of the model to represent how that might change going forward. Okay. If we look at sort of a general summary of the ability of models, of global climate models to represent the monsoon, it's probably fair to say that most models get the general monsoon flow correct. So if you look at the flow of air in the monsoon season and look at a vertical cross-section through the atmosphere, it's getting the main large-scale processes correct. Where they start falling down is in terms of the sort of more detailed spatial and temporal patterns of rainfall. So if you look across different models, the patterns of monsoon rainfall across the Indian subcontinent are very different and don't agree with observations very much. And also the timing of that monsoon season is quite variable. And most models tend to fail to capture properly these remote connections that I was talking about, particularly the one related to ENSO and to some extent the Indian Ocean teleconnection. So if one's trying to think about variability in the monsoon, models aren't capturing those external drivers particularly well. Okay. So just to give you a quick picture of what the sort of patterns of monsoon rainfall are from these models. This is essentially showing the difference across whatever it is, 13 models, is that right? 15 models, no, 13 models, in terms of the difference between mean monsoon rainfall in the model and the observed rainfall. And as you can see, there's quite large differences in terms of the difference of the basic state of monsoon rainfall. A lot of models tend to overestimate rainfall in this region and underestimate rainfall towards the further west. But there's also quite a lot of variation between the models as well. Okay. Then if we look at temperature, models also have some quite significant biases in terms of the mean temperature. This is again the monsoon season, but if one looks at different models, different seasons, you'll see similar patterns. And some of those temperature differences biases can be quite large, the order of 2 or 3 or 4 degrees. So in terms of using absolute model results, the raw model data, one has to be very cautious about using the model outputs because of these biases. So in the case of the IGP, what we've done is essentially, rather than use the raw model output, we've taken, when we're looking at our projections, we're taking the differences between the model in the future and the model in the present day and using those changes, so we remove those model biases from our projections. Okay. Final quick look is at the model monsoon evolution, and what this is showing, again, a little bit like Richard, but averaged over the IGP region. This is a month of the year here, and this is just rainfall amount. And you can see all of these different lines are different models. With this dotted line here, essentially the observed rainfall. So most of the models get a monsoon rainfall season when you average it over the whole of the domain, but most models actually underestimate the total amount of rainfall over the wider domain. And these vertical lines are the start and end of the monsoon period. And as you can see, there's a very big difference between different models as to when they indicate that the monsoon is starting and ending. So different models have either very long or rather short monsoon seasons. Okay. And again, this is showing a subset of the models. These are observed data showing the progression of the monsoon through the months of the years and going north up towards the Himalayas and into the Himalayas. And as Richard said, what you want are the models in these bottom panels to map onto to represent those two top left pictures of the intensity of the monsoon fairly well. And and essentially what we get is that they all have a monsoon, but the details of the monsoon in any individual model can be quite different from what we'd like them to be doing. Okay. So what do we get looking forward? These are just time series showing the emerging trends in rainfall over the whole of the Indo-Gangetic Plain, and then subdivided into 3 sub-regions: the Indus, the Ganges, and the Himalayan region, which is, if you like, the source region for the rivers that provide a lot of irrigation water. And what we have here is each of these. This is to the left of the year, this is the year 2010, and that's 2100. This is essentially a mix of what's 2100 observations. This is essentially a mix of the dark panel and what the models suggest have been happening, which is the lighter panel, and that's showing the variability between the different model projections. And then the lines are the average across all of the observations, all of the models. And then going forward in time, we have the average projection for each model, for each set of models under different emission scenarios. So these are, each color here is a different emission scenario. So what you tend to see is that there's actually very little change in the model average projected rainfall, at least for the monsoon season, over any of these regions. If you had to place a bet, you'd say a slight increase in monsoon rainfall, but if you look at this band, which shows the intermodal variation, it's basically an equal chance of rainfall increasing as it is decreasing. So there's a very uncertain signal in in rainfall over these areas. Thanks. For temperature, the much stronger signal of increasing temperature and a divergence between the different scenarios as one reaches the end of the 21st century. So the signal, as one has over most of the globe, the temperature signal is a much stronger signal than the rainfall signal. Okay. So what I just want to do now is show you one example of the similar analysis to those that Richard showed. And what we've got here is just one of the key crops, which is rain-fed wheat, so non-irrigated wheat. So what we're essentially looking at here is this is for the present day suitability of wheat, and the colors show the number of months of the year in which there's a suitable growing climate for that particular crop. So blue means that there's 1 month of the year is suitable for wheat growth. Purple, no month of the year or less than 1 month, and as you go up to brighter colors, a longer period of growth. And then what we have here are 2 time slices, the 2050s and the 2090s, under 3 different emission scenarios. And what we're looking at here is the average response across all of those climate models, so what we call the ensemble mean response. And essentially what you see, at least for wheat, is when it's rain-fed wheat, as you head into the 2090s, when the climate change signal is stronger, there seems to be a decrease in the number of months where the crop climate is suitable for wheat growth. So essentially what you're seeing is an expansion of the purple and the blue blocks, and a decrease in the greens, which would be a 3-month growing season. So that's assuming that it's rain-fed. If we go on to the next slide, this shows the change that you get if you assume that irrigation is actually used to support wheat growth. And here what we see is that there's a very different picture. In the present day, if you have water for irrigation, you can grow wheat virtually anywhere within the IGP. So wheat production is essentially rainfall limited over much of the domain. And as you go forward in time, through the 2050s into the 2090s, what you tend to be getting is a slight reduction in the number of months where you can grow wheat under irrigation. And what we're seeing here is a temperature tolerance signal. So as you hit the end of the century, there are some regions where it just becomes too hot to grow wheat, even if you have water available for irrigation. So just to finish off here, I think one of the interesting things that comes out of this is that the potential growing areas for many of these crops are very strongly dependent on the ability to irrigate in a future climate. And the difference between areas of rain-fed crop production versus irrigated crop production are quite marked. And then if we think about the sources of irrigation, then we've got quite a complex system of rivers that are draining the Himalayas with quite an uncertain signal in terms of the timing of irrigation water and how that propagates through to feed groundwater, which is actually the main source of irrigation water over much of this area. So it's a complicated picture and is critically dependent on water management, essentially, rather than on climate. I think
Thank you very much both to Richard and to Mark. And we'll now put our seats in the middle, and this is the opportunity for the question and answer session. Okay. Thanks. Okay. To kick off, in the back, please.
Thanks, Richard. Is that working? Is it working? Okay, I'll just talk it. Okay. So you had some interesting patterns in terms of mean rainfall patterns in the Sahel and East Africa. What can you say? Is there any consistency what the models say about variability, both seasonal variability and interannual variability, and the likelihood of occasional extreme dry events and the probabilities of those shifting over time?
There have been some pretty useful studies in the case of East Africa. I would say, before I answer the question, that I don't think that there's nearly enough work done on those couple model data sets to be able to satisfy ourselves properly with those sorts of answers, Yvinder. Each of them is as complicated as the observed to understand, and we only get a few years through the IPCC cycle before the next such data set arrives, and the CMIP5 data set is being built at the moment. So by the time those models fade off the scene, we've got a very partial understanding of what they do. In the case of East Africa, there was a nice study led by Declan Conway, which looked at the Indian Ocean dipole and showed that half the models produced an effect in one direction and the others in another direction. So precisely where that convection lands in the case of the Indian Ocean has very great implications in the case of topographically mixed region like East Africa, and therefore it's quite difficult to work out. What's going to be new about the CMIP5, the next generation of such models, is that there's a component which includes regional models, the Cordex project, which we expect will handle the topography of the region a little bit better. And early indications are that there's some rich surprises in that with respect to East Africa. For example, a lot of the coupled models might show the East African region getting wet, but not as many of the regional models once you put the complications in. So it's a tough test. The models are in some ways a great achievement of science. In other ways, they've got a long way to go.
But before we move on to the next question, I'd like to remind any of our online viewers that if you'd like to ask a question, just type it into the chat box at the bottom of your browser window. And I think we have one now.
We have one online question, yes. And it's a viewer saying, I'd like to know what the definition of the temperature sensitivity was for irrigated wheat in the IGP.
I can't answer you off the top of my head, so we'd have to look into the report and get the exact thresholds there. But they're taken from standard FAO databases.
Just to add on that score, for any of those who'd like to read the reports, they are available for download on the CCAF's website if you want to follow up on any of these details. Any more questions?
Well, let me try. It's concerning models and their, behavior concerning the ENSO representation, so it's well known depending on how the models are able to represent ENSO or not. So we get some interesting features reproduced, and in particular those two regions you were talking about are depending on this relationship. So did you look at this issue? So for example, these models that failed completely to either reproduce or to show changes. So is there any correlation, let's say?
Just a bit of background to add to Carsten's question about the ENSO system. Again, I think a lot of the coupled ocean atmosphere models are challenged to reproduce that mode of climate variability faithfully. And I think a lot of that may be down to resolution in the oceans, where it would be desirable to have at least a 1/4 degree in the tropical oceans to represent the atmosphere-ocean interaction properly. And of course the models don't have that. One effect of that is that in the case of the cold tongue, which sits across the central Pacific and which is key to the whole ENSO dynamic, is seen to extend much too far west in most coupled models. And in some cases it almost touches the warm pool region in the West Pacific, which is really problematic if you're interested in the precise regional response to ENSO. So we didn't look inside the particular role that ENSO plays in interannual variability. It was very much just looking at the mean fields and how those change, and that's indicative really of the amount of work that needs to be done to properly understand these large coupled model data sets. It's an obvious next step.
So I can add another question. You were talking about that aerosols are kind of included, I assume, and there are these, well, competing hypotheses saying that this decrease in Sahel rainfall is related either to aerosols or, of course, the ocean circulation. And so the question is if you're going to simulate these projections, so in what regard these aerosols do play a role. So, I mean, apart from the fact that we do not know how aerosols develop in the future. So are they included in those projections in general?
It's a bit of a mixed bag. Most of the models have some kind of aerosol signal in there, but it varies from a proper coupled sort of chemistry module within some of the models to a simple, almost like maybe we could call it a fudge factor that that estimates what the net top of the atmosphere effect of the aerosols is on radiative forcing. So again, if one really wanted to try and understand and tease out aerosol effects, one would have to pick and choose models quite carefully. And in the case of the Asian brown cloud story, we've got black aerosols or black carbon aerosols, which I think an even smaller proportion of global climate models are actually representing sufficiently well to be able to tease out those effects. And it's sort of, I would put the effect of the Asian brown cloud on Asian monsoon as being actually an area of research rather than an area where you'd be wanting to use results from models to make any sort of any projections and decisions that you'd bet your crop investment on.
Thank you, Mark. We have another question from online.
Yes, we have a question from an online viewer who had some trouble hearing what was said in the transmission, but the question is, did you recommend that we should be using specific ensembles of models in different regions?
Mark will hear that one.
I think there's a lot of the answer to that is both yes and no, and a lot depends on the resources that you have to do a good analysis of along the lines of what Richard was discussing for West Africa. So to do the kind of analysis that actually allows you to select less bad models from even worse models, or better models from worse models is actually quite resource intensive and hasn't really been done, I think, over most domains. So if you haven't done that, then essentially the alternative, I would say, is to use all the models as being possibilities that you can't rule out at this stage. And as time progresses, maybe there are some models that you can start ruling out for under specific criteria. But if you haven't done that careful analysis, then it's probably safer, this is my own personal view, to be looking at the full range of uncertainty in the models rather than picking and choosing a few models based on some hunch that you have.
Thanks again. Another online question is coming up.
Yes, so we have an online question from Colombia. Is it reasonable to use GCM data for looking at climate variability within cropping seasons? Or should we be relying on regional climate models for modeling within season crop responses?
I think you have to do both, because in the case of the regional models, the outcome is driven by the global models in any case. So the regional models every 6 hours ask what the conditions are like around their edges in order to compute the solution in the middle of the domain. So we find that the kinds of climates that are reproduced by the regional models are very sensitive to the forcing that's coming to them from around the edges. So properly you should understand both. Should you confine the study simply to global models? Well, no, not if you can help it, and I think that's really what the Cordex program is designed to help with, so that there will be a good data set across several regional models across key domains for us to study. The conclusions that I drew with respect to the coarse resolution global models in the case of Africa are that they can help to provide where more intensive studies should subsequently be done, and they can help to steer resources. This whole business of climate change impacts is severely limited by computational availability, so how fast we can compute things, and also by the number of hands that we have to have a look at the data once the computation's done. And there's competing axes of those resources mean that you really have to make some hard choices about where you go. And I think that very simple studies like the one that we've presented today can certainly help to guide where the most significant work would happen. I think it's of less significance, for instance, to get inside the middle of a domain which shows no sensitivity at all at the global scale, when you could be looking in for instance, in the northern fringes, in the case of the Sahel, to work out more precisely what the futures might be. So I think that the global models might help us to steer emphasis, priorities, resources, and the best studies will be done in conjunction with the regional and coupled models, global models.
Thank you. Any more questions from the room? But yes, there's one at the back.
Richard, you mentioned a recent Met Office model for West Africa which simulated the monsoon a lot better than previous versions. Has anyone identified any particular changes that have led to that improvement in the model physics, for example?
That's the interesting thing, is that to establish why improvements have happened in a model are extremely complicated and themselves take a lot of subsequent individual experiments. So it's sometimes the case that an improvement may be shown without the full diagnosis being understood. What happened in the case of the Met Office model, though, was that improvement came on the back of a dedicated program of African climate work funded by DFID, that's the Climate Science Research Partnership. And that really tells the story of what's gone on with respect to coupled models. Long-standing biases essentially just get neglected unless there are concerted efforts to focus on them and to undo them. And there's some biases that I could talk at length about which have been there for 20 years in the models and will no doubt be in the CMIP5 models as well. And what we need is concerted programs to get in there to put good scientists onto them to undo them. And we need field programs as well, so that we have adequate data to confront the models with. Otherwise, we're left to choose between models which are different, but we can't say which is precisely correct.
Thank you. Do we have another online question? Thanks.
Yes, in fact, we have 2 questions. I think perhaps we can take them both. So the first question is, at what point will the models be deemed reliable enough to rely on for farmers? That's the first question. And the second is, please speak to the next 10 to 20 years. Are we likely to see the big advances in the global model capabilities?
I'll take the first one. I think we have to learn from the way that farmers use forecast information, both weather and seasonal forecast information, to think about how we should be using climate change projections in a similar way. And what we know is that with a forecast, whether it's a weather forecast or a seasonal forecast, you are getting indications about what the likely outcome is going to be. We call it an outlook, for instance, but you're never going to get an accurate projection. And so so what one has to do is actually have this this process where the decisions that people make are actually changed from thinking about having optimal information to having suboptimal information, and therefore actually making decisions that are based on a spread of possibilities. And so you need to change the type of decisions that you're making to ones that are robust across the uncertainty, and use the available information to inform those decisions, but not to think that any particular projection is going to give you the exact answer. So no, I think we're never going to get that perfect set of information, but we're already at the stage where there is some information that's useful, and the hope is that more and more that a bigger fraction of the outputs of models actually become useful.
Right. And the second question was, what's going to happen in the next 20 years? I wish I knew, but one way to answer that question is to look back and say, what were things like in 1990? And from that perspective, in the last couple of decades, we've come an awful long way. We've got these marvelous data sets, which are a level playing field between the models in many respects, that allow us to do these sorts of studies. There's a great industry in the labs around the world in model building, which was really not nearly the same that long ago. We've got new approaches, for instance, in the regional modeling work, and there's a much greater focus and industry in sorting these things out. But of course it's going to take resources. Computing power is being delivered in greater amounts, but we're becoming aware of the extent to which this is such a big problem that it's beyond the community as it currently stands. So one view is that we might stop messing around trying to find things like the Higgs boson and put some serious money into climate science, because it is an established real problem that's in front of us, and be able to undo some of those uncertainties that we've spoken about and difficulties in the models that are so long-standing. Put differently, we wish that we could leverage the kind of funding that goes in some parts of physics for this kind of work, and we should be able to, given the immediacy and reality of the problem.
Thank you, Richard. We have another online question.
Yes. So there's a question specifically to Richard saying, in addition to biophysical qualities of plants, crop suitability has a lot to do with farmers' practices, managing microclimates. So could you speak to the absence of farmers' management practices as limitation in how these models can be used to inform policymaking and adaptation efforts?
Yeah, clearly, absolutely important. Clearly a crucial part of the equation, which takes us back to the question that Mark answered last. about how we deal with the uncertainties in the climate models, given that they're not going to go away. It's very much a two-way partnership. This study very clearly did not consider any sort of practices and mitigation practices that could be exercised. It was purely seen from the climate perspective, which is important too, because we got to know what's in front of us when you reduce the problem down in dimensions. So the study is limited because it was not real in the sense that it doesn't include those things, but it's useful in the sense that it shows us what the climate side of the story is. But this solving this issue is very much a two-way partnership, and it goes right down to that scale on the ground, the microclimate scale on the ground, about which I have to say I'm not an expert.
Thank you. We have a question from the floor.
Related to that question, what sort of questions do you think need to be answered by researchers who are perhaps able to ground truth, go to the communities that are potentially, the farming communities that are potentially experiencing these changes, in order to understand what actions need to be adopted to improve their resilience?
That's a hard question. I'll have a brief go at it. From a climate science perspective, which is of course how I see life, we're always interested in how people deal with information that's in front of them, and we're interested in where that information can be successfully used. So the test case here really is on seasonal timescales, rather than running a very long-term experiment bound up in climate change. And there's been lots of good work done there in connecting seasonal prediction, seasonal forecasting information on the ground with the way that people weigh up the choices, and the way in which we can put mechanisms in place to make the use of that information worthwhile, so the microinsurance and so on. But again, that's at the fringe of my areas of expertise. Perhaps Mark would like to add to it.
No, I think I'll just echo that a lot of what we've been showing here is 20 or 30 years in the future. And even at that stage, it's in some instances it's hard to see an emerging climate change signal that you can actually detect against uncertainty. So a lot of the shorter term approaches must be around building capacity to cope with current climate shocks and variability. And I think it's almost like a conventional wisdom that if you build resilience to existing variability, you, at least for the near-term future, you're going to be building in resilience to an emerging climate signal. There's a question sort of longer term as to whether you hit thresholds where current methods of enhancing resilience actually become redundant. But I think in most instances we're talking decades or many decades in the future, unless we see some quite sort of threshold type responses in the climate system that we're not actually seeing in the climate models, except perhaps with the Sahel being the one example where if people had adapted their agriculture to cope with rainfall variability in the 50s and 60s, that may well have been maladapted for the 70s and 80s. In fact, that's what we saw in terms of famines. So there's a danger there, but there's a lot that can be gained, I think, by actually improving coping capacities using current experience, but not locking yourself into a way of operating that makes you maladapted as the climate change signal actually emerges.
Thank you very much. I think we should stop there. We're reaching the end of our hour. So I'd just like to take this opportunity to thank our speakers in particular for their excellent presentations, and to all of us joining us both in the room and online today. The climate model performance reports from East Africa, West Africa and the Indo-Gangetic Plains that you've heard about now are available to download from the CCAF's website. And we also look forward to seeing you, hopefully, for our next science video seminar on the 18th of April at 2:30 Central European time in the afternoon. And that one will be on pest and disease research within the context of climate change. So thank you all very much. Bye-bye.